Pure gold is slightly reddish-yellow in color, but colored gold in various other colors can be produced. Colored golds can be classified to three groups: alloys with silver and copper in various proportions, producing white, yellow, green and red golds, typically malleable alloys; intermetallic compounds, producing blue and purple golds, as well as other colors. These are typically brittle but can be used as gems and inlays. Surface treatments such as oxide layers. Pure 100% gold is 24 karat by definition, so all colored golds are less than this, with the common being 18K, 14K, and 9K. Alloys. White gold is an alloy of gold and at least one white metal, usually nickel, manganese or palladium. Like yellow gold, the purity of white gold is given in carats. White gold's properties vary depending on the metals and proportions used. As a result, white gold alloys can be used for many different purposes, while a nickel alloy is hard and strong and therefore good for rings and pins. Gold palladium alloys are soft, pliable and good for white gold gemstone settings, sometimes with other metals like copper, silver, and platinum for weight and durability, although this often requires specialized goldsmiths. The term white gold is used very loosely in the industry to describe carat gold alloys with a whitish hue. It is a common misconception that the color of the rhodium plating, which is seen on many commercial pieces, is actually the color of white gold. The term white covers a large spectrum of colors that borders or overlaps pale yellow, tinted brown, and even very pale rose. The jewelry industry often conceals these off-white colors by rhodium plating. A common white gold formulation consists of 90% gold and 10% nickel. Copper can be added to increase malleability. The strength of gold-nickel-copper alloys is caused by formation of two phases, a gold-rich OCU and a nickel-rich NiCu, and the resulting hardening of the material. The alloys used in jewelry industry are gold, palladium, silver and gold-nickel-copper. Zinc, palladium and nickel act as primary bleaching agents for gold. Zinc acts as a secondary bleaching agent to attenuate the color of copper. The nickel used in some white gold alloys can cause an allergic reaction when worn over long periods. This reaction, typically a minor skin rash from nickel dermatitis, occurs in about 1 out of 8 people, and because of this, many countries do not use nickel in the white gold formulations. Rose, red, and pink gold. Rose gold is a gold and copper alloy widely used for specialized jewelry. Rose gold, also known as pink gold and red gold, was popular in Russia at the beginning of the 19th century, and was also known as Russian gold, although this term is now obsolete. Rose gold jewelry is becoming more popular in the 21st century and is commonly used for wedding rings, bracelets, and other jewelry. Although the names are often used interchangeably, the difference between red, rose, and pink gold is the copper content. The higher the copper content, the stronger the red coloration. Pink gold uses the least copper, followed by rose gold, with red gold having the highest copper content. Examples of the common alloys for 18K rose gold, 18K red gold, and 18K pink gold. 18K red gold, 75% gold, 25% copper. 18K rose gold, 75% gold, 22.25% copper, 2.75% silver. 18K pink gold, 75% gold, 20% copper, 5% silver. 12K red gold, 50% gold and 50% copper. Up to 15% zinc can be added to copper-rich alloys to change the color to reddish yellow or dark yellow. During ancient times, due to impurities in the smelting process, gold frequently turned a reddish color. This is why many Greco-Roman texts, and even many texts from the Middle Ages, describe gold as red. Rose gold. The highest carat version of rose gold is also known as crown gold, which is 22 carat. 18 carat red gold may be made of 25% copper and 75% gold. For 18 carat rose gold, typically about 4% silver is added to 75% gold and 21% copper to give a rose color. 14 carat red gold is often found in the Middle East and contains 41.67% copper. High-end flutes are very commonly made of solid rose gold, the most common alloy being 14K. Span gold. Some gold-copper-aluminium alloys form a fine surface texture at heat treatment, yielding an interesting spangling effect. At cooling, they undergo a quasi-martensitic transformation from body-centered cubic to body-centered tetragonal phase. The transformation does not depend on the cooling rate. A polished object is heated in hot oil to 150 to 200 degrees Celsius for 10 minutes, then cooled below 20 degrees Celsius, forming a sparkly surface covered with tiny facets. The alloy of 76% gold, 19% copper, and 5% aluminium yields a yellow color. The alloy of 76% gold, 18% copper, and 6% aluminium is pink. Green gold. Green gold was known to Lydians as long ago as 860 BC under the name electrum, a naturally occurring alloy of silver and gold. It actually appears as greenish-yellow rather than green. Fired enamels adhere better to these alloys. Cadmium can also be added to gold alloys, but there are health concerns regarding its use. The alloy of 75% gold, 23% copper, and 2% cadmium yields light green 18 karat gold. The alloy of 75% gold, 15% silver, 6% copper, and 4% cadmium yields a dark green alloy. Gray gold. Gray gold alloys are usually made from gold and palladium. A cheaper alternative which does not use palladium is made by adding silver, manganese and copper in specific ratios to the gold. Intermetallic. All the O2 intermetallics have crystal structure of calcium fluoride and therefore are brittle. Deviation from the stoichiometry results in loss of color. Slightly non-stoichiometric compositions are however used to achieve a fine-grained 2- or 3-phase microstructure with reduced brittleness. A small amount of palladium, copper or silver can be added to achieve a less brittle microstructure. The intermetallic compounds tend to have poor corrosion resistance. The less noble elements are leached to the environment, and a gold-rich surface layer is formed. Direct contact of blue and purple gold elements with skin should be avoided, as exposure to sweat may result in metal leaching and discoloration of the metal surface. Purple gold. Purple gold is an alloy of gold and aluminium rich in gold aluminium intermetallic. Gold content in Ural-2 is around 79% and can therefore be referred to as 18 karat gold. Purple gold is more brittle than other gold alloys, as it is an intermetallic compound instead of a malleable alloy, and a sharp blow may cause it to shatter. It is therefore usually machined and faceted to be used as a gem in conventional jewelry rather than by itself. At a lower content of gold, the material is composed of the intermetallic and an aluminium-rich solid solution phase. At a higher content of gold, the gold-richer intermetallic coral forms. The purple color is preserved to about 15% of aluminium. At 88% of gold, the material is composed of aural and changes color. Blue gold. Blue gold is an alloy of gold and either gallium or indium. Gold indium contains 46% gold and 54% indium, forming an intermetallic compound or An2. While several sources remark this intermetallic to have a clear blue color, in fact the effect is slight, or An2 has CIE lab color coordinates of 79, -3.7, -4.2, which appears roughly as a grayish color. With gallium, gold forms an intermetallic AuGa2 which has slighter bluish hue. The melting point of An2 is 541 degrees Celsius. For AuGa2 it is 492 degrees Celsius. An2 is less brittle than AuGa2, which itself is less brittle than Al2. A surface plating of blue gold on carat gold or sterling silver can be achieved by a gold plating of the surface followed by indium plating, with layer thickness matching the 1:2 atomic ratio. A heat treatment then causes interdiffusion of the metals and formation of the required intermetallic compound. Surface treatments. Black gold. Black gold is a type of gold used in jewelry. Black-colored gold can be produced by various methods. Electroplating, using black rhodium or ruthenium. Solutions that contain ruthenium give a slightly harder black coating than those that contain rhodium, patination by applying sulfur and oxygen-containing compounds. Plasma-assisted chemical vapor deposition process involving amorphous carbon, controlled oxidation of gold-containing chromium or cobalt. A range of colors from brown to black can be achieved on copper-rich alloys by treatment with potassium sulfide. Cobalt-containing alloys, e.g., 75% gold with 25% cobalt, form a black oxide layer with heat treatment at 700 to 950 degrees Celsius. Copper, iron and titanium can be also used for such effect. Gold-cobalt-chromium alloy yields a surface oxide that's olive-tinted because of the chromium oxide content, is about 5 times thinner than ochre and has significantly better wear resistance. The gold-cobalt alloy consists of gold-rich and cobalt-rich phases. The cobalt-rich phase grains are capable of oxide layer formation on their surface. More recently, black gold can be formed by creating nanostructures on the surface. A femtosecond laser pulse deforms the surface of the metal, creating an immensely increased surface area which absorbs virtually all the light that falls on it, thus rendering it deep black. But this method is used in high-technology applications rather than for appearance in jewelry. Blue gold. Oxide layers can also be used to obtain blue gold from an alloy of 75% gold, 24.4% iron, and 0.6% nickel. The layer forms on heat treatment in air between 450 to 600 degrees Celsius. A rich sapphire blue-colored gold of 20 to 23 K can also be obtained by alloying with ruthenium, rhodium and 3 other elements and heat treating at 1800 degrees Celsius to form the 3 to 6 micrometers thick colored surface oxide layer